Right, hi. Example number 2. The structure uses this structure over here. Okay, it uses a 10 by 10 millimeter bar and 25 millimeter cable to support the load P. Okay, so AC, okay, given that BC, this is the bar, and AC, this is a cable. Okay, so this is what we've been given. And then we draw transformation X and Y. Rotation is about Z. Okay, so we are given that the bar BC is made of yield strength 300 megapascal, Young's modulus of 200 gigapascal. Okay, so what I did down here is we calculate the area of ABC and AAC. So this is our ABC and AAC. Okay, so while cable AC is made of high strength steel, this is a yield strength and this Young's modulus. We have to determine whether the structure can support the load of 250 kilonewton at this end over here, at the point C. So only consider in-plane buckling, with safety factor of 2, and the yield of the steel is 1.5. So I've broken those down. So these are the yield strength for BC. So this is a structure AC over here. It's a cable. And we are given that factor of safety for buckling is 2. Factor of safety for non-buckling is 1.5. So we're going to do this analysis, we're going to assume, or not assume, we're going to perform thrust analysis. So when we declare this, we only consider axial loading. Okay, we only consider axial loading condition, and then we're going to apply method of joints. At point C, okay, to find the axial forces. Okay, so method of joint, very straightforward. I hope you'll remember. This is our point C. We have a load coming down, and this is 250 times 10 to the power 3 Newton. And then we have two axes. We're sticking the axial load. One is in this direction, and the other one is in the other direction. And over here, this is our AC line. This is our BC line. So we know from here, member AC can take the axial loading. The vertical loading. So this is our AC Y, and because it's vector, this is our AC X. This is our FAC. And if you look at the member AC now, so this is our member AC. Action equal reaction. So we know that member AC is under what? Tension. Okay, so let's deal with AC first. So we do static analysis. Positive is going up. Right? So ACY minus by 250 times 10 to the power 3 is equal to 0. ACY is equal to 250 times 10 to the power 3 Newton. So we know ACY and we can find ACX directly. Okay, so we know the distance. One is 3, the other one is 4. So we can use similar triangles. So 250, right? So we can use ACX over 4 is equal to ACY over 3. So ACX will be equal to ACY. This is equal to 250 times 10 to the power 3 multiplied by 4 over 3. So this will be equal to 250 power 3 times by 4 over 3. 250 power 3 times by 4 over 3. So it's equal to 33.333 times by 10 to the power 3 Newton. Okay, so that's your ACX. So now once you can find your ACX, you can find your FAC, which is square root of 250 times 10 to the power 3 squared plus by 333.33 times 10 to the power 3 squared. Okay, so 250 power 3 squared plus by 333.333 power 3 squared, square root of the whole thing is equal to 416.667 times 10 to the power 3 Newton. So from here we know the analysis that member AC is under tension. So i.e. we don't need to do a buckling analysis, because buckling you have to go through what? Compression. Okay, so member AC, you no need to go through buckling. So the next thing from here, we are going to do the next analysis. So we are aware that BCX has to be opposing ACX, right? So from here, remember BC will be under compression mode. So why this direction? Because of Newton's third law, action equal reaction. So this is going through what we call compression. So from here, we know that we're going to do summation about forces. In the x direction is equal to 0. So it's equal to minus ACX plus by BCX is equal to 0. From here, we know that BCX is equal to, we'll calculate 333.333 times 10 to the power 3 Newton. And we also know that member BC is under compression. So when it's under compression, we know that BC, there's a possibility of BC failing in buckling, so must perform buckling analysis. Okay, so I like this question. This is like a typical a design engineer, what they have to do when actually designing a structure. You have to consider whether it will fail by under axial loading or will it fail by under buckling loading. So these are the factors that you have to consider. So let's consider member AC. Which is, for this case, is the cable under tension. Right? So failure will occur right when the stress, maximum stress, is greater than stress allowable. Okay, so stress max for this case, so our AC, our forces, is equal to 416, positive 416.667 times 10 to the power 3. Area of the cable, which is 490.874 times 10 to the power minus 6. So this will be equal to 416.667 power 3 divided by 490.874 power minus 6. It's equal to 848. Wow, this is quite high. 848.826 times 10 to the power 6 Pascal. And then the stress allowable. So we are given that the stress yield is going to be at 1,800. divided by the safety of factor. So safety of factor of the steel is 1.5. So 1.5, this is not due to buckling, okay? This is due to standard conventional failure. So it's equal to 120 times 10 to the power 6 Pascal. Hallelujah. So what we realize that, therefore, right? So therefore, stress max is lower than stress allowable, right? So common cable AC will not fail. Okay, I know we have written this down already, so we also declare no need to perform buckling analysis, right, as member AC is under tension. So now we consider member BC. Okay, so member BC is member over here, so we have to consider member BC. So same thing first. We have to check that it will not fail due to normal loading. So failure will again occur where stress max is greater than stress allowable. So stress max, so for member BC, which is equal to 333.33, times 10 to the power 3, divided by area, is equal to 10 times 10 to the power minus 3. So this is 333.33 power 3 divided by 10 power minus 3 is equal to 33.333 times 10 to the power 6 Pascal. And then the stress allowable, what is allowed by the material property, this is equal to the stress allowable, so 300 times 10 to the power 6 divided by 1.5. So 300, here 200 times 10 to the power 6 Pascal. So for this case, our stress max is less than the stress allowable. Therefore, material will not fail due to its yield strength. Okay. But we have to do another analysis, the buckling analysis. It's because it's under compression load. So we have to perform buckling analysis. So for this case, to do buckling analysis, we know that the critical load is equal to factor of safety, or factor of safety. Okay. Actual will be equal to PCR divided by P. And we have to make sure that the factor of safety of the actual must be less than 2.0. Okay, must be less than, must be greater than 2.0. If less, you will fail. Okay, then structure will not fail due to buckling. Okay, so we know that P is equal to 3.333 times 10 to the power 3 Newton. Okay, so your PCR will be equal to pi squared divided by LE squared, right? And then multiply by EI. Okay, so note that the equivalent length is also equal to the length as both ends. Okay, so both ends cannot resist bending moment. So what does this mean? I.e., both ends are pinned. Okay, so this is what it means. So we just declare both ends are pinned. Okay, both ends are pinned. Okay, so when that's the case, we can calculate. So therefore, PCR is equal to pi squared multiplied by 200. No, this one is 190. Am I right? Is it 190? Maybe I got it wrong. I remember the 190 rings a bell. Yep, 190. No, for the, that's the cable. For the youngs is 200. Do apologize. 200 times 10 to the power 9 divided by LE. So the length is 4 meters, and the second moment of area. Okay, so multiply by power 4. Why power 4 is BD cubed over 12. The breadth and depth are the same. Okay, so this will be equal to, I'm just too freak-minded now, sorry. So 0.1 power 4 divided by 12 times by pi squared times by 200 power 9 divided by 4. So hold on, shift pi, sorry, squared over here, times by 200 power 9 divided by 16 times by 0.1 power 4 divided by 12. So it's equal to 1028.084 times 10 to the power 3 Newton. Okay, so therefore the actual factor of safety is equal to 1028.084 times 10 to the power 3 divided by 333.333 times 10 to the power 3. So this is equal to 1028.084 power 3 divided by 333.333 power 3. It's equal to 3.084. So what we seen down here is the factor of safety for the actual is greater than 2.0. Okay, therefore structure will not fail due to buckling. Okay, so that's where we are now. So I'll stop the lecture on buckling and we'll continue again. Okay, thank you.